Okay, so looking at polynomials algebraically, we spend time talking about them graphically, looking at a picture of the graph and being able to determine different parts of the graph. But now what we want to do is be able to analyze these polynomials only by looking at the equation. So a couple questions to keep in mind here. What's the difference between a zero and a factor? So these two terms are actually very closely related to one another. If I've got a function, and I'll leave it in like factored form, I've got x plus 1 times, I don't know, x minus 2. The idea here is that x plus 1 and x minus 2 are factors of this polynomial. Okay, if we were to multiply them out, this would, again, this is the same thing as x squared minus x minus 2. So x plus 1 and x minus 2, those would be factors of this polynomial function right here. But what a 0 is, it's a value that when I plug into the function will give me 0 back as my solution. So for example, if I were to plug in -1 or +2 into this function here, then those would give me 0 as my result. Therefore, I would say the zeros of my polynomial function would be -1 and 2. The factors of this polynomial function would be x plus 1 and x minus 2. So you can see that there's a relationship that exists between zeros and factors. Next up, but just by looking at a polynomial function, the equation, not the graph, how can we tell how many zeros we could have? This is all based upon the degree of the polynomial. So the idea here is if I've got a function, say, I don't know, x to the 5th power minus 4x to the 4th minus 3x cubed plus 7x squared minus 5. I'm just making up some sort of polynomial. All we need to do is figure out how many zeros could we possibly have is by looking at the degree of my leading term in standard form. So what we'll say is that the degree of this polynomial is 5 because 5 is the highest power of one of my terms. So I'm asking, well, how many zeros could we possibly have? We could have at most 5, which again is the degree of the polynomial. What does it mean to have imaginary zeros? Basically, what that means is that if you have a polynomial function and you try and factor it out, find out what the zeros are, and you end up with something that is unfactorable, we can try throwing it into the quadratic formula. Now, if we end up throwing into the quadratic formula and we end up with a negative number underneath the radical, well, that means that we end up with what are referred to as imaginary zeros. Okay, so if I have something like, I don't know, x squared plus 4, I can't factor this. If I try throwing it into the quadratic formula, I'll find that I end up with a negative number underneath the radical. And so therefore, I would have what are referred to as imaginary zeros. Now, what does that look like on our graph? Well, you're not really going to be able to see it. If we have zeros on our graph, as we point out before, kind of coincide with our factors, and they also play a big role into our x-intercepts as well. So if I had a 0 at, say, like 2, that means at the point 2 comma 0, there would be an x-intercept. When I have an imaginary 0, because it's an imaginary number, it's a non-real number, you aren't going to see it occur on our graph. And then the next question we have is here, is it possible to have only one imaginary 0? Well, the answer to that question is no, because once again, if I'm throwing something into the quadratic formula, negative b plus or minus b squared minus 4ac all over 2a, again, where are these imaginary numbers coming from? Well, they're occurring when the number underneath the radical is going to be less than 0, when it's negative. And the idea here is if I end up with a value that's negative underneath here, I'm going to have a plus or minus out in front of that value. So there's actually going to be 2 of them. Therefore, it will be impossible for there to only be one imaginary 0. So when we're talking about end behavior, we're talking about what happens to the graph as we move further and further along the x-axis in the positive direction towards positive infinity, and what happens as it moves further and further to the left towards negative infinity. Now, you'll notice here I used LC plus or minus. LC stands for leading coefficient, because we're going to be looking at 2 different things. We're going to be looking at the degree of the polynomial, whether it's even or odd, as listed right here, but we also want to pay attention to the leading coefficient. Is the leading coefficient positive or is it negative? Now, in the event that we have an odd degree polynomial, you're going to notice that as we move in either direction, the end behavior is going to be different in either negative or positive infinity. We have an odd degree polynomial and the leading coefficient is positive. As we move further to the right, our function is going to go towards positive infinity. As we move towards the left, it's going to go towards negative infinity. However, if we have a negative leading coefficient with an odd degree polynomial, as we move towards positive infinity, it's going to move towards negative infinity. And as we move towards negative infinity on the x-axis, it's going to move towards positive infinity. So this applies for every single odd degree polynomial with a leading coefficient of whether it's positive like we have up here or whether it's negative like we have down here. So when we have odd degree polynomial, the end behavior is going to be in opposite directions, plus minus, minus plus. Even degree polynomials are a little bit easier to remember because they're both going in the same direction. So when we have a leading coefficient that's positive with an even degree polynomial, they're both going to go towards positive infinity. When we have a negative leading coefficient, however, they're both going to go down towards negative infinity. So evens are pretty easy to remember because all you have to remember as well is it positive or is it negative, and then both will be going down, up or down towards that direction. Okay. So using these rules here, we can very easily determine the end behavior of a polynomial without even knowing what the graph looks like. So in this first one here, f of x is x to the fourth plus 3x cubed minus 2x plus 1. We really don't even need to know what's going on over here. All I need to know is what's the leading coefficient. There isn't anything written, so I can assume that it's a positive 1. And I know that the degree is even. So if I remember my rules, leading coefficient is positive, the degree is even, so I would expect both of these functions to go the function to go towards positive infinity in both directions. Moving on to the second one, positive leading coefficient, odd degree. So as we move towards positive infinity, this is going to move up towards positive infinity, and as I move further to the left, it's going to go towards negative infinity. Number 3, we got a negative leading coefficient and an even degree. So both are going in the same direction. Negative leading coefficient leads me to believe that both of these are going to go towards negative infinity. And then finally, we have a positive leading coefficient, even degree. Once again, we're going up towards positive infinity in both directions. So next up, we want to find x-intercepts. And in order to do that, what I'll encourage you to do to start off with is try to factor from the very beginning. It'll make things very easy for you when it comes time to find your x-intercepts. So for the first one, number 5, hopefully that one isn't too difficult. We got x squared minus 3x minus 4. So I'm looking for two numbers that when added together give me negative 3, but when multiplied together give me negative 4. That's going to be negative 4 and positive 1. So when I go through and I solve, okay, x is going to equal 4 and negative 1. But once again, I want to find the x-intercepts. X-intercepts are written as coordinates. So my coordinates are going to be 4, 0 and negative 1, 0. I can repeat this process here. I've got 3x squared minus x minus 4. Once again, same concept. However, with the leading coefficient being something other than 1, it might be a little challenging depending upon the problem. Well, I know that one of the terms over here has to be 3x. The other one has to be x. Those are the only two values that are going to multiply together to give me 3x squared. And I need two numbers that when multiplied together give me negative 4, but when added together give me negative, give me negative 1. So when I'm looking for that, I believe we are going to end up with a negative 4 over here and a positive 1. So 3x squared for the first terms. 3x times 1 is positive 3x. Negative 4 times x is negative 4x, so that'll give us the negative x. And then negative 4 times 1 will give us the negative 4. So my values for x are going to be, and again, these are set equal to 0. X should be equal to 4 over 3 and negative 1. But if I'm writing them as x-intercepts, I want to make sure I write them as such. So that's going to give me 4 over 3, 0, as well as negative 1, 0. Number 7, you see that we have 4 terms here. We can actually factor by grouping together the first 2 terms and looking to see what we can pull out of those groupings. So in a 2x cubed minus 4x squared, I think I can pull out a 2x squared out of that. And when I do that, I should be left over with an x minus 2. For the second one, I can pull out a positive 5. And that once again gives me an x minus 2. So now when I factor, I just need to pull the two terms that are on the outside. So 2x squared plus 5 will be my first grouping. And then what they have in common over here is going to give me x minus 2. So now when I set those values equal to 0, okay, well, now we run into an interesting case, because if I take 2x squared plus 5 and set it equal to 0, I'm going to get x squared is equal to negative 5 halves. And if I try and take the square root of that, well, I can't do that, because then I'll end up with an imaginary number. So we actually aren't going to get any real numbers from this solution. Therefore, I won't be getting any x-intercepts from this particular 0. However, for the second factor, x minus 2, I end up with a real solution 2. So I end up with an x-intercept at 2, 0. Therefore, my only answer should be at 2, 0 when it comes to x-intercepts. Finally, we have number 8 with 8x cubed minus 27. Hopefully you recognize that this is a difference of perfect cubes, okay? So for those of you who might not be familiar, we've got these formulas for the sum and difference of perfect cubes, okay? For those of you who might not remember, again, write the formula as plus and minus over here. You can follow the formula with following along with the sign. So if it's a cubed plus b cubed, you'll follow the sign that's on top. If it's you follow the one that's on the bottom, all the other signs will be on the bottom. What I mean by that is that's going to give me a plus b, a plus or minus b, a squared minus plus ab plus b squared. So what I was mentioning before, if it's a cubed plus b cubed, the factorization will be a plus b times a squared minus ab plus b squared. If it's a cubed minus b cubed, it'll be a minus b times a squared plus ab plus b squared. And for those of you who might remember this acronym, we've got the acronym SOAP, which describes which signs we're looking at when it comes time for the factorization of the sum or difference of perfect cubes. So it stands for same, opposite, always, positive. So looking at just, let's pretend it's a cubed plus b cubed. A cubed plus b cubed, you'll notice that the first set of parentheses, a plus b, the sign is the same. We've got plus here and a plus here. Similarly, if it was a cubed minus b cubed, I would have a minus b. That's where the s comes from. The next part is opposite, and that's when we move into the second set of parentheses. So notice if it's a cubed plus b cubed, we're looking at the top sign. In here, in the second set of parentheses, it's minus. Similarly, if it's a cubed minus b cubed, minus out here, well, it becomes a plus over here. And then finally, always positive, we always add b squared at the end of it. So when I'm trying to factor this out, 8x cubed minus 27, what I'm going to want to do is plug these values in for a and b. Now, what I like to do is I like to just take the cube root of both of those numbers. So I want to take the cube root of 8x cubed, and I also want to take the cube root of 27. Notice that I'm not necessarily throwing the negative sign in front there. I'm just finding the cube root of the number and then plugging the b value into the appropriate formula. So the cube root of 8x cubed is just 2x. The cube root of 27 is 3. So 2x will be my a value. 3 will be my b value. This is a difference formula. So when I plug it into the formula, this will be my a value, 2x, minus b, so 2x minus 3, a squared, so 2x, that entire value squared should give me 4x squared. And now I move to the opposite sign. I was subtracting, so therefore I'm going to want to make sure I add over here. A times b, well, 3 times 2x should give me 6x. And then I'm always positive. I'm always adding b squared. 3 squared is going to give me 9. So now if I want to find the x-intercepts, the first one should be easy. It's just setting 2x minus 3 equal to 0. I end up getting x is equal to 3 halves. So my first x-intercept would be 3 over 2, 0. But the second one, you'll notice that it looks a little complicated. You actually won't be able to factor this out. You will never be, anytime you're working with the sum or difference of perfect cubes, you'll never be able to factor out the second set of parentheses. So the best we can do is to plug it into the quadratic formula. So we've got negative b plus or minus the square root of b squared minus 4ac all over 2a, for those of you who might have forgotten. Plugging these values here, a is going to be 4, b is going to be 6, c is going to be 9. This is negative 6 plus or minus the square root of 6 squared minus 4 times 4 times 9. And now what we're going to do is put that over 2 times 4. And what we take a look at, just the value underneath the radical here, this is going to give me 36 minus 16 times 9. What's going to happen is I'm going to end up with a negative value underneath my radical. And because of that, I'm actually not going to get any real zeros for this particular solution. So for this factor here, the 4x squared plus 6x plus 9, I'm actually not going to be able to get any x-intercepts. Therefore, my only solution is 3 over 2, comma 0. So now over on this page, it says, well, what happens if we can't factor? And we kind of touched on it on the last problem. If you're dealing with a quadratic, why not use the quadratic formula? Once again, negative b plus or minus the square root of b squared minus 4ac all over 2a. So I have 2x squared minus 3x minus 4. So my a value is 2, my b value is negative 3, and my c value is negative 4. Plugging this in, it looks like I have 3 plus or minus the square root of 3 squared minus 4 times 2 times negative 4 all over 2 times 2. So simplifying that, it looks like I have 3 plus or minus the square root of 3 squared is 9. Let's see here. Negative 4 times 2 is 8. And negative 8 times negative 4 is a positive 32. Okay. All over 4. So it looks like if I clean that up a little bit, that will be 3 plus or minus the square root of 41 over 4. These are my two solutions here. Unfortunately, there's nothing we can do to simplify the square root of 41, nor is there any way we can simplify some things out. So for our solution, we'll just say that the first x-intercept is going to be 3 plus the square root of 41 over 4, comma 0. And my second one will be 3 minus the square root of 41 over 4, comma 0. Can do the same thing over here for number 10. It looks like my a value is going to be 1. So here's a, b value is 2, c value is going to be 10. So negative b would give me negative 2 plus or minus the square root of 2 squared. So that would give me 4 eventually, minus 4 times 1 times 10. And this is all going to be over 2 times 1. Now, just looking what's underneath the radical here, if I simplify, this is negative 2 plus or minus the square root of 4 minus 40. Well, right away, I notice that I'm going to end up with a negative value underneath my radical. And because of that, I'm going to end up with an imaginary solution. So if I end up with an imaginary solution when solving through trying to find my zeros to help me get my x-intercept, what's going to happen is that there are going to be no x-intercepts. Once again, in order for there to be x-intercepts, there needs to be a real number when we go through and use the quadratic formula. So next up, we've got putting it all together. We're going to find the x-intercepts and the end behavior in order to graph the polynomial. We can kind of get a pretty decent sketch without even really looking at our calculator. So first and foremost, what's going to happen here is I know that I've got a positive leading coefficient and an even degree. So I know that as I move further to the left, my function is going to be going up. And as I move further to the right, I should also be going up. And now it's just a matter of figuring out, well, where are my x-intercepts to kind of give me an idea. I can take number 11 and factor. This will actually be x plus 3 times x minus 7. And when I go through and solve, I get x is equal to negative 3, and it's also going to be equal to 7. So my x-intercepts are going to be at negative 3, comma 0, as well as 7, comma 0. I could find the y-intercept by setting x equal to 0, and if I do that, I'll get 0 squared minus 4 times 0 minus 21. So I would expect my y-intercept to be at 0, comma negative 21, that's going to be all the way down here. So again, just using what I know about this function, the end behavior and the x-intercepts, well, as I go towards the left, I would expect my function to be coming from the top over here. And as I move further and further to the right, it should also be going to the right. So just very rough sketch. And again, clearly not the best drawing, but we can get a pretty decent look at this graph without even looking at an actual picture of the graph, just using what we know about the end behavior as well as the x-intercepts. So for these next two problems, the number 12 is actually nice because it's already factored out for us. So we would expect there to be an x-intercept at 2, 0, and we would also expect there to be one at negative 3, 0. But one thing I want to do is I'm going to rewrite this as x minus 2 times x plus 3 quantities squared. And the reason I'm doing that is because if you notice, we have an factor of x plus 3 here, factor of x plus 3 here. There's what's referred to as a multiplicity of a factor, okay? And what I'm going to say is that anytime we have an even multiplicity, so for example, this one is x plus 3 quantity squared, if it's being raised to an even power like 4, 6, or 8, what's going to happen is that our graph is actually going to touch at that particular function, at that particular x-intercept set, I should say, sorry, and it's going to go back in the direction it came. So it actually isn't going to pass through to the opposite side of the x-axis. Now, using what we know about end behavior as well, if I multiply all these out, eventually I would end up with x to the third power as my leading term here with a leading coefficient of 1. So positive leading coefficient, odd degree, I know my function should look something like this with a middle portion moving around. So using what I know about my function, I would expect there to be an x-intercept at negative 3, I'm sorry, put that in the wrong spot, negative 3. And I also expect there to be one at 2, 0. If I want to find my y-intercept, I could plug in 0 for x, so that would give me, so that would be what, negative 2 times 3 times 3, so that should give me a negative 18. So I would expect there to be a y-intercept somewhere around here. So just doing what I use about my graph, again, I'm coming from negative infinity, odd degree, positive leading coefficient. And as I mentioned before, it's got a multiplicity of 2. So what's going to happen in my graph is it's going to touch this x-intercept and it's going to go back down towards my y-intercept. But then once again, as it comes back up, it's going to touch that x-intercept and come all the way back up again. And I know this isn't the prettiest looking graph, but you can confirm this result just by looking at your calculator. Similarly, with number 13, we've got a sum of perfect cubes. So my a value should be x, my b value should be 2. Again, just taking the cube root of both of those numbers, plugging it into the formula, that should be x plus 2 times x squared minus 2x plus 4. Again, this is from the sum of perfect cubes formula. Therefore, I would expect a value, x-intercept at negative 2, 0. I can't factor the second set of parentheses. However, I can throw it into the quadratic formula. That'll be 2 plus or minus the square root of 2 squared minus 4 times 1 times 4. And as you may have already noticed here, that I will get a negative value underneath the radical, so I can expect that there won't be any real zeros from this particular quadratic. So I don't have to even worry about another solution. I know, again, a odd degree, positive leading coefficient. So from negative infinity should be coming down. As it goes towards positive infinity, it'll be going up towards positive infinity. I mark off my graph here. I could also plug in my y-intercept by plugging in 0 for x. So 0 cubed plus 8 should give me 8. That gives me a much nicer number. So here's my y-intercept at 8. I've got my x-intercept here at 0. So if I were to graph my function, it would probably look something like this, give or take. As long as the points make sense and the graph is going in the appropriate direction, that's fine. I'm not going to grade you on how good your curves fit because, as you can see, it's clearly not a talent of mine.